Hello, students. Welcome back to our chemistry class. Let me ask you a curious question. Why does a chilled soda bottle fizz so much the moment you open it? Or why do fish thrive better in cold rivers than in warm ponds? The secret lies in today's fascinating concept, the solubility of gases in liquids, particularly in water. Now, solubility of a gas means the maximum amount of that gas which can dissolve in a fixed amount of liquid under particular conditions of pressure and temperature. This idea is not just a textbook definition, it governs aquatic life, controls the fizz in our favorite drinks, and even plays a role in industrial processes. And the principle that governs it is beautifully explained by something we call Henry's law. At constant temperature, the amount of gas that dissolves in a liquid is directly proportional to the pressure of the gas above the liquid. This statement is known as Henry's law. In symbolic form, we express it as C equals K times P, that is, concentration C equals Henry's constant K multiplied by pressure P. For instance, when carbon dioxide gas is forced into water under high pressure while bottling soda, a large amount of carbon dioxide dissolves. That is why your soda remains fizzy as long as it is sealed. But the moment you open it, the pressure outside reduces and the dissolved carbon dioxide escapes as bubbles. You can almost visualize this equation in action. C equals Kp when you hear that familiar hiss while opening a cold drink bottle. Let's take the soda water case more closely. Inside the sealed bottle, carbon dioxide is dissolved under high pressure. The liquid looks calm and clear. But when you twist open the cap, the external pressure drops suddenly. According to Henry's law, solubility drops too. The excess carbon dioxide cannot stay dissolved anymore, so it escapes rapidly, forming bubbles. This is why we say carbon dioxide dissolved in water produces carbon dioxide gas bubbles when the bottle is opened. That sparkling fizz is nothing but the chemistry of pressure and solubility unfolding right before your eyes. Now let's turn to temperature. The general rule is that as temperature increases, the solubility of gases decreases. Why does this happen? At higher temperatures, molecules of gas gain more kinetic energy. This extra energy makes it easier for them to escape from the liquid into the air. That's why, when you heat water, dissolved air escapes and you may even see small bubbles clinging to the vessel before boiling starts. We could say, gas dissolved in hot water produces gas molecules that quickly escape into the air. So, temperature and solubility share an inverse relationship. When one goes up, the other comes down. This is why gases are always more soluble in cold water than in hot water. Have you noticed that a chilled soda fizzes far more vigorously than one kept at room temperature? That's because more carbon dioxide is dissolved at the lower temperature. As soon as you open the chilled bottle, the sudden release of excess gas creates a stronger fizz. On the other hand, a warm soda tastes flat because most of the gas has already escaped. The same principle explains why fish and aquatic animals flourish better in cold lakes and rivers. Oxygen gas, which they depend upon, dissolves more efficiently in colder water than in warm water. Nature, as always, follows chemistry's rules. Henry's law is not just theoretical, it has practical calculations and applications. Imagine the pressure on a liquid surface doubles. According to C equals Kp, the solubility of the gas will also double provided temperature remains constant. That's the mathematical beauty of this law. But it also explains phenomena like decompression sickness or the bends, which divers face when nitrogen dissolves in their blood under high pressure underwater. If they rise to the surface too quickly, the rapid drop in pressure causes nitrogen bubbles to form in their bloodstream, a dangerous situation. On the positive side, Industries use Henry's law to carbonate soft drinks and beer, maintaining them under high pressure and low temperature for maximum gas solubility. So, whether it's your soda can or a diver's safety, Henry's law is at play. So, let's wrap this up. We have learned that the solubility of gases depends strongly on two factors: pressure and temperature. According to Henry's law, at constant temperature, solubility is directly proportional to pressure, meaning more pressure means more gas dissolved. On the other hand, when temperature rises, solubility falls because gases escape more readily. This explains everything from the fizz in our soda to the survival of aquatic life to industrial carbonation and even medical challenges like decompression sickness. I hope this session helped you realize that chemistry is not just about equations like C equals Kp, but about living processes and daily phenomena happening all around us. Remember, chemistry is the invisible force behind what we drink, how we breathe, and even how we enjoy a chilled soda on a hot day. See you in the next class with more fascinating insights from the world of chemistry.